Good morning. Let's see. So those of you in Merck's class, your midterm was due yesterday, so hopefully it wasn't too terrible and you all survived. Today is our FAM day. Since I'm talking about family, it's our FAM day. But today is our day we talk about stuff in FAM's class, and that's how he started talking about probability things. So I suppose I should ask, what kind of questions do you guys have? And we can certainly talk about probability, but we can also talk about other things like integration by parts, partial fractions, all the kind of integral stuff as usual. So what do you want to talk about? Also, here's the usual attendance and tutoring links. Oh, also, actually, before I mean, you're welcome to ask questions whenever, but I know I sent you guys all an email about the, wow, there are words in my head. I sent you all an email about the end of quarter evaluation, and that's the evaluation of this class. If you could all please do it when you have a chance, I would greatly appreciate it. So the link is there's an announcement, I sent you an email, and let me also just give you the link right here as well. So let me grab that. So here's the link to the evaluation. It's just like 5 questions where you just pick an answer to each question. It should only take like a minute or 2 at the most. If you guys could all please do that when you have a chance, I and my boss would both really appreciate it. Let me do one thing here. Cool. So, do you guys have questions, things you want me to talk about, or should I just start? Oh, sorry, I do see a question. Can we do a little more practice with the tabular method? Of course we can. In fact, so the nice thing about the tabular method, maybe nice, I don't know. The thing I think is nice about the tabular method on occasion is that there are only very specific times you can use it. We'll do an example with kind of each one of the ones, and then there's kind of the easy versions and then the harder versions, which we can also do. So, don't be too excited, but I got new pens. I am super excited. Also, if you look back, this way, I'm trying to point to it. If you look right there, you can see the pile of pens I have, right? It's like, I think I have like 12 boxes of pens, so I'm very excited about pens. Yes, Jalissa, we can certainly start going over probability as well. But let's start with the integration by parts tabular stuff because that's the older stuff, and then we can start going over probability. Hopefully the noise calms down outside. I know the other thing I wanted to say was I also posted in the announcements a link to the fall quarter co-classes. And actually, you know what? I know I posted that for us. Let me look at one thing real quick. I just want to make sure. I don't know if we actually offer a Co-16C in the fall, so let me double check. I don't want to get your guys' hopes up about that. So I feel like we usually don't, but I feel like I should know. Let me take a look real quick here. So let's see. Co-16 do not offer a Co-16C. Well, that's lame. So here's what I'll say about Co-16C. Well, because I won't say, I guess. Right? So there is no Co-16C in the fall. I don't imagine that will change unless there's a lot of students who are asking for it. And even then, it's probably not likely because we have a lot more teaching to do with the AATC in the fall because we teach the pre-16 classes. That said, I will still be very available, as will the other instructors or the other specialists during the fall. I will also say we're probably going to be more available over the summer, right? Like during the summer, we don't have any teaching responsibilities. We don't teach any co-classes or pre-classes. So if you're kind of debating whether to take 16C over the fall or in the summer, I might recommend summer just because you'll have access to me and Grant and Sarah and oh my gosh, Claire and Duff and Casey. will be much more available in the fall. We actually are going to have specific hours set up to be there. So if you're thinking about doing it in the summer, I would probably push you in that direction and say you should take it in the summer versus taking it in the fall, because at least from my point of view, I'll be able to help you more in the fall. So just some food for thought. I'll probably post something on campus as well, just for people that aren't here to see that. But in fact, let me write myself a little note so that I remember to do that. 16C, fall versus summer. Okay. Yeah, I think if you guys have the option, I would probably pick summer, or even at community college, that's also a cheaper option. So that's something to consider as well. I know it's not exactly the same, but it's still not a bad option if you are thinking about doing it. Okay, so the tabular method. So the tabular method, oh man, new pens. I'm so excited about the new pens, I'm not gonna lie. I was definitely, my pens were getting kind of terrible. You guys are like, this guy's super excited about pens. I am, it's nice to write with nice pens. So the tabular method you can use for 3 and only 3 types of integrals. X to a power, so like x to the 5th times sine of x, or I suppose I'm gonna, yeah. So there's actually, or x to a power times cosine of x, or x to a power times e to the x. Now a couple things. One, it has to be a positive power, so it can't be a negative power, it can't be I should say, so it has to be a positive integer power. And the other thing is, oh no, that's really it. And then it's got to be sine, cosine, and e to the x. Now, they can be slightly more complicated. You could have something like this, like x to the 5th times sine of 3x. And you can have some coefficient of x there, and that will also work for tabular method. And then you could even be something slightly more complicated, although I feel like this would be kind of terrible. You could have something like, you could have like something like x cubed. Wow, that's a 2, not a 3. You can have something like 2x cubed plus x times cosine of 2x. That would be kind of the most complicated, I think, a tabular method could be. In any event, it's always going to be the same process. You're always going to make a table, that's why it's called the tabular method, where one column you let u be the x thing, whether it's this thing or this thing, right? And it's a polynomial. And then you're going to let dv be the other thing, either the trig thing that's sine or cosine, and only sine or cosine, or the e to the x thing. So let's do some of these easy ones, and then we'll do some of these harder ones. And we'll see that they're not too awful. And so the thing I will remind you or mention is that the higher the power of x, or the higher the degree of your polynomial, the more steps you're going to have to do, the longer your table is going to be. Right, so let's do this one first. This one's going to be the shortest one. If I was going to do the integral of x cubed times cosine of x dx, I'm going to make a table, and I'm going to let u equal. And so I usually write it more like this. I say, here's my u, and u is going to be x cubed, and here's my dv, and dv is going to be cosine of x. It's really cosine of x dx, but when we're doing the tabular method, we don't usually write the dx part, although you certainly could. So on the u side, I'm taking all the derivatives. All right, we're doing derivatives. So the root of x cubed is 3x squared. The root of 3x squared is 6x. The root of 6x is 6. The root of 6 is 0. If you're doing the tabular method, the u column, if you're taking derivatives, you should always get to 0 at the end. If you don't get to 0, it means you should not be using tabular. You made the wrong choice for you. So once again, doing tabular, whatever you pick for u should be a polynomial with a positive integer power of x, and its derivative should eventually be 0. And then on the dv side, we're going to just do the same number of entries, taking the anti-derivative. This is where for the trig function ones, you have to be kind of extra careful, because the signs are always the opposite of what they should be. Right? So I know the derivative of cosine is negative sign, and the anti-derivative of cosine is positive sign. and the antiderivative sign is negative cosine of x. The antiderivative negative cosine of x is positive, is negative sine of x. And then the antiderivative negative sign is positive cosine. We should always cycle through 4 different things. So if you start at cosine, you should go all the way through sine, negative cosine, and negative sine, back to cosine again. Right, so what I'm trying to say is, like, you shouldn't have gotten cosine here, right? Because you didn't do enough things. And from sine to the next sine, they should always be kind of going back and forth between the positive and negative one. That might be different if you have an interesting coefficient of x here, but we'll talk about that in the next example. So after you've made your table, then you just have to say, okay, it's plus this times this. It's minus this times this. It's plus this times this. It's minus this times this. It always starts with a plus and always alternates like that. So my answer here is going to be plus, and I wouldn't normally write the plus out or whatever, x cubed times sine of x minus 3x squared times negative cosine of x plus 6x times negative sine of x minus 6 times cosine of x plus c. And with enough practice, you can kind of just figure, like, if I was actually writing out my answer, I would have been like, okay, it's x cubed sine of x minus a minus is plus 3x squared cosine plus a minus plus times a minus is minus 6x sine x and a minus. So you really should write this out as x cubed sine of x plus 3x squared cosine of x minus 6x sine of x minus 6 cosine of x plus c. Right, that's how we should really write out the answer. So that's the idea here with the tabular method, is you're just writing, you're picking your u to be whatever power of x, picking dv to be the cosine sine of e to the x, and then you're doing this process. So let's do at least a couple more, because this is really useful when you can use it. I left my water in the other room. I'll grab it. So actually, that gives me a good opportunity. So why don't you guys try doing this next one on your own? So I want you all to use the tabular method to integrate. I'm going to give you the probably a somewhat easy one, I think. X to the 4th e to the x dx. So make your u table, make your dv table or column, and then do that. And I'm going to go grab my water. You guys should do this one. It shouldn't be too bad. I'm very excited about my exams, yes. I know. Okay. My wife was just saying it's very funny. I'm excited about my independence. So here, you should be what? What's you going to be, everybody? Yeah, thank you, Sophia. So you use x to the 4th, and then just take all the derivatives, and I do want to write the 0. 4x cubed is the first derivative, and then 12x squared, and then 24x, and then 24, and then 0. And then e to the x is kind of the nicest choice for dv ever, because all the antiderivatives are e to the x. You almost don't even need to write it. This one, there's no weird signs to deal with, so I just know it's going to be plus. It's going to be plus, minus, plus, minus, plus. So this one's super straightforward. It's going to be x to the 4th e to the x minus 4x cubed e to the x plus 12x squared e to the x minus 24x e to the x plus 24 e to the x plus c. Right? That's, I mean, if you did this the long way, this is I think this is on the edge of maybe too many steps. Like I could see maybe asking this on a test, but I feel like it's kind of too long to ask on a test. But if you did this the long way, you would be hurting, right? You'd have to do iteration by parts 4 different times, and that's just way too much. It's really, really easy when you're doing, if you're actually like doing it the long way, where you let u be this, and dv be this, and write uv minus v du. Eventually, it's really easy to get caught up and miss how a sign might affect something. Okay, so these are the quote unquote easier ones where it's just x to a power and either sine, cosine, e to the x. So you get a little more challenging when you have like e to the something times x or something like that. So let's look at a version like that. And I think we could probably fit one in right here. So let's look at something like, let's not make it too crazy. Let's do x squared times e to the -1/2 x dx. Yeah, that's a good problem. So same sort of choice we're going to make. We're going to let u be the algebraic thing, the x to a power, and dv is going to be the e exponential thing. So my u column is going to be x squared, and the derivatives are 2x, 2, and 0. dv is going to be e to the -1/2 x. That's my first dv. And then I have to anti-differentiate that. So when I anti-differentiate e to the -1/2 x, what am I going to get? And I feel like I asked that question. So I'm going to get e to the -1/2 x. And then what do I have to divide by? Right? If I'm anti-differentiating e to the -1/2 x, what am I dividing by? Yeah, I'm dividing by -1/2, which is the same as multiplying by -2. So while you could write divide by -1/2 here, I think it's better just to write, oh, I know I'm going to times by 2. And then here's the nice thing about this. Once that happens, the same thing happens every step. Right? When I anti-differentiate to the next step, this constant just hangs out, right? It's a constant multiple. So when I anti-differentiate this again, I get e to the -1/2 x times -2 times another -2. I get e to the -1/2 x times 4. And then I get, when I anti-differentiate again, I get e to the -1/2 x. Yeah, my -1/2 times x is terrible. Most people would probably write this as e to the -x/2. So this was quite as awful. Let me write that. And then this one would be e to the -x/2 times a -8. Because each time you anti-differentiate that, you have to divide by another factor of -1/2, which is the same as multiplying by another factor of -2. So then we throw it all together, plus, minus, plus. And here I can see that each one is going to end up being negative, right? Because there's a negative factor here, so it's plus this times this, which is going to be negative. Then it's minus this times this. There's no negative sign here, so it's just a minus something. And then it's plus this times this, but there's a minus sign. So I can see that overall it's going to be, all the terms are going to be negative. And then I'm getting, let's see, x squared times e to the -x/2 is -2. So I'd probably write that as -2 x squared e to the -x/2. And then I'm going to get minus 2x times 4 is going to be 8x times e to the -x/2. And then my next one is going to be minus 2 times 8 is 16 e to the -x/2 plus c. And these tabular ones always kind of follow the pattern of it's just decreasing powers of x, right? Because you're literally decreasing the power of x every time you differentiate, times whatever your function is, either e or e to the whatever, or if it's your trig function, sine or cosine. Let's do one or two more. Because I know it's kind of a lot, but I do think this is a valuable method to be aware of. I would definitely ask a question on a test that was like integrate x cubed times cosine of 2x or something like that, because it's certainly doable the long way. It just takes time, but it's much easier the short way. So let's do the integral of x cubed sine of 5x dx. 5x, yeah, let's do 5x. Negative 5x for a second, but we'll leave it at 5x. All right, I'm just doing the usual tabular thing. There's my u, it's x cubed, my derivatives. And then so I will say, especially for sine and cosine, I feel like it's where we have to be a little bit extra careful when teaching the antiderivative. So if my dv is sine of 5x, what's the antiderivative going to be? First of all, let me ask you, is it going to be positive cosine or negative cosine? You can just put a plus or a minus in the chat if you want. Yep, you guys are on top of it. Negative cosine of what? Just x? No, of course not. right, is that the whole story? Is there anything else I need to do? Yeah, I need to either multiply by 1/5 or divide by 5. When I'm doing this, I kind of like, I don't know, either way is really fine. I think I'm partial to saying divided by 5. Now that I write it like that, I feel like it's terrible. Let's just say times 1/5, which I would normally probably write in front, but whatever. And then the next antiderivative is the same sort of thing. So I'm going to anti-differentiate negative cosine. I'm going to get negative sine. I also know it's going to be negative because it should be the opposite of this. And then I have the 1/5, and then I have another 1/5, which I'd probably just write as 1/5 squared. And then I do it again, and the antiderivative of negative sine is going to be positive cosine. Another factor of 1/5. And then I have to differentiate this, and I get sine of 5x times 1/5 to the 4th. Okay. And then we have a plus, a minus, a plus, a minus. So it's, let's see. So I was going to try to write this up all at once. It's going to be negative here. So it's negative x cubed times cosine 5x all over 5. And then negative negative is positive. 3x squared times sine of 5x. All over 5 squared, which is 25. And then this one's going to be positive, right? Because it's 6x times this into the positive. So plus 6x times cosine of 5x. You are welcome, right? Like you could totally write this as 1/5 times x cubed cosine of 5x or negative 1/5. You write this as 3/25 times x squared sine 5x. Either way is really perfectly fine. I'm just writing it like this because I find it convenient. This is going to be 6x times cosine 5x over 5 cubed, which you could just leave as 5 cubed, or if you know what it is. Finally, this is going to be a minus 6 times sine of 5x over 5 to the 4th, which is 625. Let's see. But again, if the numbers that you're writing, if the powers get too big, just leave it as like 5 to the 4th or whatever. Okay. Let's do one more, because I do think it's worth seeing this. Like, I don't really kind of usually think about these other ones, but you can definitely have a thing where where like the u choice isn't just an x to a power, but it's actually a couple terms, right? It's like x to a power plus another thing. Let's try one like that, and then we'll call it a day. So we just did sine, right? Yeah, okay, let's make it extra special. So let's do the integral of, let's see. Let's do, I don't want to do too many steps. Let's do 3x squared plus 8x minus 2 times sine of negative 2x. Yeah, that's gonna, this would be, I mean, it's still not that bad, but it's kind of gross. But the choices here are obvious. I mean, or they should be obvious after this practice, right? And so I feel like, I mean, if I was doing this integral, I wouldn't immediately think integration, or I mean tabular method right off the bat, because it just looks less typical. But then I would be like, oh yeah, I have polynomial in x times a sine or a cosine or an e or whatever. That's the only time I get to use tabular. If that, I mean, you could also break this up into 3 different integrals. 3x squared times sine of negative 2x, 8x times sine of negative 2x, and minus 2 times sine of negative 2x. And you could do tabular for each of those, but that's not what you want to do. You want to let u equal the whole thing. Which I know is weird, but whatever. And then the derivatives are 6x plus 8, and then 6, and then 0. And my dv's are, well, sine of negative 2x. Okay, when I anti-differentiate this, I'm going to have to divide by negative 2. So it's going to be negative cosine of negative 2x divided by negative 2. I might just make that a plus plus so that I can see that. So this is, so then actually this is kind of where we have to be super extra careful. Right? If we're going to anti-differentiate cosine of negative 2x, it's going to be sine of negative 2x, but divided by another negative 2. So it's going to be sine of negative 2x divided by a 2 times another negative 2 is going to be a negative 4. And then I feel like my columns are a little bit off from each other, right? So this is time. Sometimes I start to do this. I make sure that things stay in line with each other. So the antiderivative of this, the antiderivative of sine, is going to be negative cosine of negative 2x divided by negative 4 times another negative 2 is negative 8. And then I would make this. Right? So sometimes when you have a negative on the inside, especially with the trig function, you kind of get to be extra careful with the signs. And when I say signs, I mean S-I-G-N-S, not S-I-N-E-S, the pluses or minuses. So then plus this times this, minus this times this, plus this times this. And it's going to be a little bit ugly. So do I have enough room? Yeah, kind of. So let's see. So I have this times this. Yeesh. So I would probably not do much simplifying here. I'm just going to write it as, yeah, all right, 1/2 times 3x squared plus 8x minus 2 times cosine of negative 2x. If this had happened, if I had picked something that was like an even number here, I probably would distribute the 1/2, right? Like if this was a 4x squared, I would distribute this and get 2x squared plus 4x minus 1. But it's not, so I won't. The next one is going to be, let's see, I see a minus and another minus. It's going to be a plus 1/4 times 6x plus 8 times sine of negative 2x. And then I see a plus, and I see just pluses here, right? There's no minus or minus. So I see a plus 1/8. I would probably write it. So here, 1/8 times 6 is going to be 3/4. So I would write it as either 6/8 or 3/4 cosine of negative 2x. Let's see. So that's kind of the most extreme version of a tabular method question. Again, not too awful, but it does get a little bit messy. So, questions about this tabular stuff, or is there anything you still want me to say about tabular, or do you think we've covered it pretty well? I think we've covered it pretty well, but if there's something else you want me to say, happy to say it. No, that's dumb. I suppose there's one more thing I think I should say. So, okay. The other thing I want to say is sometimes you'll have a definite interval with tabular. By the way, here is the, so I'm gonna sorry, let me grab one thing real quick here. Here is the usual stuff, which I'm now including the end of the quarter evaluation on there. So there are the links to the attendance, the tutoring, and the end of quarter eval that I would really appreciate everyone doing sometime before the end of the quarter, which I know you have still a couple weeks left. So, come on. Sorry, I'm just doing weird things here. Okay. So the one other thing you might see sometimes is a definite interval where you have to do tabular method first. So let's say we had something not too terrible. Let's make it, let me think for 1 second here. Yeah, we should do that. Okay, let's do the integral from, yeah, let's not make it too lawful, James. 0 to pi x squared sine of x dx. So this is definitely a good time to use tabular because I don't personally, and I think most people don't, like having to do integration by parts where you're carrying the limits of integration through the whole process. Like I don't want to write this as some u times some v evaluated from 0 to pi minus the integral from 0 to pi of v du. And then, right, it gets messy. So when I have a definite integral and I know my integration process requires more than just a straightforward find the antiderivative, this is when I like to do the indefinite integral on its own and then go back here. So I would do the indefinite integral, and I'm going to do the indefinite integral using the method that makes the most sense, which is tabular method here. So here are my derivatives. Here are my antiderivatives. So I got sine of x. Antiderivative is negative cosine of x. Antiderivative is negative sine of x. Antiderivative is cosine of x. Right? Looks right. Plus, it's a minus, it's a plus. So my antiderivative is looking like x squared times negative cosine of x. So I'm going to write that as negative x squared cosine of x. Minus a minus is going to be a plus. It's going to be plus 2x times sine of x. Plus 2 times cosine of x. Evaluate between 0 and pi. And then we have to plug things in. So we're going to get, let's see, negative pi squared cosine of pi plus, now here's where it's good to know. I could go ahead and write out 2 times pi times sine of pi, but I know, and hopefully you guys know, that sine of pi is 0. If you don't remember, here's the unit circle. Wow, okay, well, let's try that again. Here's the unit circle. And over here, right, here's the point 1, 0, 0, 1, negative 1, 0, 0, negative 1, where the x coordinate is cosine and the y coordinate is sine. And the angles are theta equals 0 radians, theta equals pi over 2 radians, theta equals pi radians, and theta equals 3 pi over 2. And here, theta is also 2 pi. So then we can actually, in fact, let's go back and deal with cosine pi as well. Cosine pi is negative 1. Sine of pi is 0, so this term is just going to be 0. And cosine of pi is negative 1. Minus, if I plug in 0, plugging in 0 is even easier. 0 squared is 0. 2 times 0 is 0. 2 times cosine of 0 is 2 times cosine of 0 is 1. So let's see what we get. We get negative pi squared, and the negative is on the outside, right? So it's not negative pi quantity squared. It's negative pi squared. Times negative 1 is going to be a positive pi squared minus 2 minus 2, which is pi squared minus 4. And that would be the amount of area under the curve x squared times sine of x from 0 to pi. So that's not too terrible. But again, I would definitely do the antiderivative and then be like, okay, now I have to plug in the limits of integration. All right, I think we've talked enough about tabular method here. So let's go ahead and move on to talking about this probability stuff. So let me actually grab some examples that I know I have. So let's see here. Where'd you go? 1 second, please. Man, I had a whole bunch of stuff. Where did I put you? Sorry, I'm always hiding some stuff on the computer. See, there's just a million things up here. All right. So yeah, let's talk about all the regular things. So we'll talk about expected value, variance, standard deviation, and kind of where we go. If you have specific questions, feel free to pipe up. But I'll just kind of go with what I've got. So a lot of this stuff, or at least the first thing we're talking about here, I think should be relatively like common sense stuff. Like I think most people, even if they don't know the terminology, they do know what an expected value is. It's just another word for average. So for example, if I want to find, it's kind of a dismal, so the example that I have written here, that someone else wrote, is find the average of these test scores. And there's 2 zeros, 2 hundreds, an 80, and a 20. And I guess they're probably numbers that work out well, but I would hope those were never actual test scores that we saw, because I don't want people getting zeros. So find the average, which is just another word for expected value of these test scores. And so the test scores are 0, 0, 100, 100, 80, and 20. Which you might be able to see already that the average is going to be 50. right, because if you think of these, like the average of these is 50, the average of these is 50, and the average of these is 50, it's kind of neat. But here's how we calculate the average. So here's some notation. We can write the average as x bar, or we can write, so there's like lots of notation terminology for the average, x bar or mu or capital E of x. Those are all different terminologies or notations for writing the average for the expected value. Oh my gosh, come on. And the way you're going to do that, another word for this is the weighted average. You're just going to add all the scores up. And divide by the total number. So here you're going to get 100 plus 100 plus 80 plus 20, which is 300 over 6, which is 50. Another way of calculating this, which actually does make sense, is to think about the number of times each score occurs, or I should say, the value of each score occurring times the probability that you see it. So another way you could write this is, well, this is really, I'm going to break this up as 0 over 6 plus 0 over 6. I know this seems kind of silly, but just check it out for a second. So if I think about the probability of selecting a particular test score, well, there's 2 zeros, so there's a 2 out of 6 chance I pick someone that got a 0. There's 200, so there's a 2 out of 6 chance I pick someone that got 100. There's 180 and there's 120, so there's a 1 out of 6 chance of picking someone with 180. There's a 1 out of 6 chance of picking someone with 20. So I can reframe this as, and I want to write like that, yeah, 0 times 2 6 plus 100 times 2 6 plus 80 times 1 6 plus 20 times 1 6. It's still the same math. You're still getting the same exact numbers. But the reason you might write it like this is because then it's more clear that you can see that the expected value formula, right? Because we're going to eventually see things where we don't just know how many times each thing occurred, but each thing is going to occur with some probability. So we're going to say, oh, look, this is just the expected value of x is the value of x, right? We're seeing that, right? These are the x values. This is like x1, x2, x3, x4, x5, and x6. So the expected value of some random variable x is, I don't want to write this yet, I like this, is the values of x times the probability that those values occur. So x1 is 0, the probability that x1 occurs is 2 6. X, and then so, sorry. Sure, I guess I could, sorry, my notation got a little bit wonky here. I suppose I should, since these are the same, I should be calling both of these x1s, both of these x2s, x3 and x4. So if x1 times the probability of x1, it's x2 times the probability of x2, plus x3 times the probability of x3, plus x4 times the probability of x4. So in general, when you're trying to find the expected value of some variable, it's the values of that variable multiplied by the probability that that value occurs, and then you add all those up. And oftentimes you'll see people write this with the sigma notation, which means you're just adding everything up. So this is, wow, that's terrible. This is the sum, in this case, from I equals 1 to 4, right, because there's 4 different things, of x sub I times p of x sub I. And that just means exactly, right? So what this really means, I don't know how familiar you guys are with this notation, but it means you plug in I equals 1, so you get x sub 1 times p of x sub 1, and then you're done with 1, so you add, right? That's what this big sigma means, and then you go to the next, I equals 2, oh, I get x sub 2 times p of x sub 2. Then I add, and you plug in 3, I get x sub 3 times p of x sub 3. And then I add, and I get x sub 4 times p of x sub 4, and I stop at 4 because that's my upper limit there. So that's what that notation means. This thing here and this thing here are exactly the same. I got a little bit dizzy. Let me give you guys the attendance and the tutoring and the end of quarter eval one more time. So generally, for some random variable x, I should say, for some discrete random variable, and there's a difference between discrete and continuous. So for a discrete Already covered this pen. The problem is I get a new black pen. I'm like, yeah, it's too bright and nice and dark black all the time. So let's use blue for a while. So discrete, random, variable, x. I got my notation for just 1 second here. Yeah, sure. Has expected value, which is again another word for the mean or the average. It's x of 1 times the probability that x of 1 occurs plus x of 2 times the probability that x of 2 occurs plus all the way up until the last value, so x of n times the probability that x of n occurs, which we can write as the sum from I equals 1 to n of x of I times the probability of x of I. This is the typical way of writing the expected value or the mean. I feel like before I do that, I should give you another example. Let me just do my favorite example. So there's lots of examples of this. One of them is rolling a die. So rolling 1 6-sided die. I know what I want to say. Die, I forget if die has an E or not. I don't care. So what I want to mention, oh yeah, I was talking about discrete. So a discrete random variable is a variable that only takes on a finite number of different values. So rolling a die is definitely one, right? There are only 6 different outcomes that can happen. Or flipping some number of coins, right? If I flip 3 coins, there are 8 different things that can happen, or really depending on, well, it depends on what you define to be your outcome, right? If I flip 3 coins and I say the number of heads is my random variable, then there's 4 different things that can happen, like 0 head, 1 head, 2 head. But the idea is that when we talk about something discrete, there are only a finite number of distinct options for the outcomes. Whereas continuous random variables, which we definitely are going to get into, are things that can have an infinite number of possible values. And things that people often think about like this are like if you're measuring the amount of time it takes for something to happen, right? There are an infinite number of possible times that can actually occur. Now, sometimes we limit that and say, well, we want to just measure it to the nearest minute, and then it becomes discrete. But technically, right, you can have the time be some number of minutes, seconds, milliseconds, et cetera, et cetera, et cetera. Or you could also talk about like the height of a person. There are literally an infinite number of heights that a person could be, or the weight of a person, or anything where you can kind of, where the degree of measurement can be as fine as you want it to be. Those things are usually continuous random variables because you can always dig down and say like, well, there's really kind of an unlimited number of possibilities. So discrete, finite number of possibilities, continuous, infinite number of possibilities. So if I'm rolling 1 6-sided die, let's figure out what the expected value of that's going to be. Well, there are 6 sides, and each side has an equal probability of being rolled. So each side has a 1/6 probability. So the expected value is going to be, well, let's see, I can roll a 1, and the probability that's going to be 1/6, or a 2, the probability 1/6, or a 3, probability 1/6. I don't know why I think it's in there, or a 4, the probability 1/6, or a 5, with the probability 1/6, or a 6, with the probability 1/6. And I will again point out, this is the same as just calculating an average, right? I'm thinking about rolling a die, each thing is equal to probability. So I'm saying, well, I could get a 1 plus a 2 plus a 3 plus a 4 plus 5 plus 6 divided by 6 total things that can happen. When I do this, I get 1 plus 2 plus 3 plus 4 plus 5 plus 6, all divided by 6. 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. That reduces to, let's see, they both have a 3, that reduces to 7/2, which is 3.5. What I really wanted to point out with this particular example is that sometimes the expected value of a thing happening isn't actually one of the things that can happen, right? You can't roll a die and get a 3.5. It just doesn't happen. But the thing is that over the long run, if we kept rolling a die, we would expect it to average out to be about 3.5, because we'd expect each thing to happen on average the same amount of times, or the same probability, and so this is what ends up happening in the end. Let's do one more expected value before we start talking about I think I've tightened my board just a little bit too much. Okay. Yeah, okay. So let's talk about flipping coins. Flipping coins and having children are kind of actually the same type of example because they're a thing where you can say, like, I'm going to flip 4 coins and record the number of heads. Or I'm going to say a couple have 4 kids and talk about the number of girls or boys. So, right, they're each things that we generally assume have a 50-50 probability of happening unless someone says something otherwise. So let's look at this example. Let's say a coin is tossed. Let's do 4 times because I know most teachers usually do 3 times. You've probably already seen that example or will see that example. Let's say a coin is tossed. The coin tossed is, no, okay. Not in English class, right? We don't care about the grammar as long as the math is correct. The coin is tossed 4 times. And the number of, it doesn't really matter if it's talking about heads or tails. Let's say the number of tails, which we'll call capital T, is recorded. Let's find the expected value. Or average number of tails that should occur when we toss a coin 4 times. Now, I'm going to jump to the end here for just a second because there's something I want you to know. When you're performing, I think it's called an experiment or whatever, when you're doing something some number of times and you know the probability of something happening, the actual way you can easily calculate the expected value is just going to be the number of times you do the thing times the probability that happens. So since the probability of getting a tail is, well, I was going to say 4, probability of getting a tail is 4. Since the probability of flipping a tail is 1/2, and we're flipping 4 coins, we would expect, and that's why we use the word expected value, we would expect to get 2 tails, right? We take half of the coins to go with tails, half of the coins to go with heads. And it actually does work that way. If I was flipping 6 coins, I would expect to get 3 tails. If I was flipping 5 coins, yes, I would expect to get 5 halves or 2.5 tails. It's not a real number or a real number of tails you can get. It is a real number. But so that's kind of a nice idea here. And that works whether you're talking about tail, flipping coins, having kids, throwing dice. So if I was going to say, if I was going to throw 2 dice, if I was going to roll 2 dice, the expected value of those 2 dice would be the expected value of each die added together. So it's going to be 3 halves plus 3 halves, which is 7 halves, right? Whoops, yeah, okay, let's go around one more time. 7 halves plus 7 halves, which would be 7. So the expected value when you roll 2 dice is 7. Okay. So back to this one. Yes, it's going to be 2, but let's actually calculate it. So I need to kind of list all the things that can happen. So I can get 4 tails. Right, tails, 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 tails. I can get 3 tails, but there's more than one way of getting 3 tails. I can get first 3 being tails and then heads, or first 2 tails, then heads and tails, or tails, heads, tails, tails, or heads, tails, tails, tails. So, let's just keep going. Let's talk about 2 tails. Actually, let's go over. So the nice thing about 3 tails is it's the same number of ways of getting 1 tail. In this example, right? Because if I'm getting 3 tails, I'm saying, well, there's 1 head. Well, so now I'm kind of interchanging the role of heads and tails, saying, well, I'm getting 1 tail, I'm getting 3 heads. So I can write this as 1 tail is going to be heads, 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 tails, heads, heads, tails, heads. I'm just literally interchanging every tail. Or, sorry, my brain just went away. Heads, tails, heads, heads, or tails, heads, heads, heads. So 4 ways of getting head, 3 heads, 1 head, 3 tails. 4 ways of getting 3 heads, 1 tail. 1 way of getting 4 tails. 1 way of getting 0 tails. And then there's 2 tails. So here's how I usually do something like this. I kind of think about moving the thing of interest from right to left. So I'm going to start off with heads, heads, tails, tails. Because when you start having more than one thing and you have kind of lots of spaces, it can be easy to not figure out if you've gotten all of them. So I typically write like this, and then I think about this one just moving over one spot at a time. I'm saying now I'm going to heads, tails, and then tails, heads, heads. I'm just moving that one over. And then I'm exhausted how many times I can move this one over. So then I move this one over and move this one back. So I can have now heads, tails, heads, right? Because now they're both starting as far right, but not at the end spot. I move this one over one, so tails, heads. And then I move this one over as far as I can, so then I move this one over and I have tails, heads. 1, 2, 3, 4, 5, 6 ways to get into tails. And that's all the ways I can get this, right? There's 1 plus 1 plus 4 plus 4 plus 6 is 16. And there are 16 different things that can happen, because if I'm thinking about flipping 4 coins, 1, 2, 3, 4, there are 2 possible outcomes for each coin. So there's 2 times 2 times 2 times 2, which is 16 possible outcomes. So we definitely listed them all. And now we can make a table with the probabilities, which you will often see in this class. So let's list X, the value, or I really should say T, X, I think X. X here is the number of tails, and T of X is the probability of getting that number of tails. So we can have 1 tail, or sorry, we have 0 tails, or 1 tail, or 2 tails, or 3 tails, or 4 tails. So let me ask you guys, what's the probability of getting 0 tails? There's a couple things I should say, but I'll wait a minute. Yeah, exactly, 1 out of 16. And it's exactly, so let me say a few things that I haven't said. In an example like this, in most examples, the probability of getting the thing you're asking about is the number of ways you can get it out of the total number of things that can happen. So it's exactly 1 out of 16. Just like in this previous example, the probability of rolling a 3 is 1 out of 6, because there's one way to roll 3 out of 6 things that can happen. So generally, or kind of basically, when we're talking about probability, typically the way we calculate probability is just it's the number of things that you want to happen out of the total number of things that can happen. So using that same idea, what's the probability of getting 1 tail? Well, how many ways can you get 1 tail? 4 ways. Out of how many ways? 16 ways. So 4/16. And then let me ask you guys, how many ways can I get 2? What's the probability of flipping 2 tails? I know it's easy, but okay, yeah, 6/16. How about the probability of flipping 3 tails? Someone. Yeah, sorry, I couldn't. Yeah, 4/16. And then finally, the last one's going to be 1/16. A couple things that are true that we should always be aware of when it comes to probabilities of things happening is the probability of any one thing happening should always be between 0 and 1. The probability of something happening can't be less than 0. There can't be a negative probability of something happening. And the probability of something happening can't be greater than 100% or greater than 1. So our probability should always be between 0 and 1. And the sum of the probabilities, right? If I add up all the probabilities, which I'm using right, kind of, sometimes we're lazy and we don't write this up. If I add up all the probabilities, it should add up to 1. If you look at the probability of all possible things happening, it should be 100%. And it is. 1/16 plus 4/16 plus 6/16 plus 4/16 plus 1/16 is 16/16, which is 1. So that's a good check that we know that we've actually done this right. If you're missing, like, if these don't add up to 1, means, like, for like, we could have said, for example, maybe I missed one of these and only got 5 tails, 5 was even 2 tails, and I got 5/16 there. And if I added them up and got 15/16, I'd be like, oh no, I must have missed something somewhere. I should go back and, I should go and check. And then specifically for things like number of tails or heads or number of boys and girls, where there's a 50-50 chance, typically the probability table is symmetric, right? We're getting 1/16, then 4/16, then 16/6. The S's are killing me. Then 6/16, then back to 4/16, then back to 1/16. So there's a nice kind of symmetric pattern where we're going where you're starting low on the ends and then going up towards the middle. I'm trying to like do this like that. It's very much like a bell-shaped kind of thing. Fact, is there a picture that I have for you guys? No, there's not. Okay. All right, so we can actually ask a lot of questions. But let's go ahead and do the expected value first, just to show you that it really is what we said it was. But it is generally true, right? I'm not just like saying this particular example. It is generally true that if a random variable, I should be a little more careful. But typically, you can multiply the number of trials by the probability of something happening to get the expected value. And I know that formula is in your book somewhere. Let me actually look now so I can reference it here. 9.1. Just so you guys know what I'm talking about. Maybe it's not in the book. I feel like it is. Maybe I'm a liar. Yeah, I could be. I know they talk about it in stats classes, but I am not seeing it in your textbook here, which I find mildly surprising. It might be in one of the problems in the textbook. It's not that big a deal, but it's kind of more big. No. Sorry. No. I guess not. Oh well. I wouldn't sweat it too much. He said he's going to stop looking for it. All right. Okay. So the expected value, I already know it's going to be 2. Let's actually calculate it. So again, it's going to be the sum of the x's times the probability of the x's. Or x in this case is the number of tails, and the probability of x is the probability of that number of tails. So we're literally just going to take this times this plus this times this plus this times this. So it's going to be 0 times 1/16 plus 1 times 3/16 plus 3/16. Are you crazy, James? It's 4/16. Plus 2 times 6/16. And yes, you could totally reduce these fractions. We just often don't. 3 times 4/16 plus 4 times 1/16. Adding these up, so I'm going to keep my denominator as 16. 0 times 1, 1 times 4, 2 times 6, 3 times 4, 4 times 1. And I better get 30. Ooh, 0 times 1. Wow, that's 1, James. 0, right? So I end up with 16 plus 16 is 32 over 16, which is 2. Just like we expected. I hope that made you laugh, because it definitely made me laugh in that. Pun very much intended there. But it literally, I mean, the reason it's called the expected value is actually because we do expect this to happen. It's not like they just made up this word, like, oh, we'll call this like, no, they literally used it because it is the actual thing we expect to happen. On average, we expect 2 tails to flip when we flip 4 coins. And then you can ask other questions like, what's the probability that the number of tails, which is x, is greater than or equal to 1? So I should really say, what's the probability that x is greater than or equal to 1? Now, in this case, you could say, well, if x is greater than or equal to 1, let's do this plus this plus this plus this. That's one way you could do it. It would be the probability that x is equal to 1, plus the probability that x is equal to 2, plus the probability that x is equal to 3, plus the probability that x is equal to 4. And then you can add up all those things, which would be 4/16 plus 6/16 plus 4/16 plus 1/16, which is 10, 14, 15, 16. But the easier way to do this is to use what's called the complement rule. Instead of saying what's the probability that x is greater than or equal to 1, I can say that's, well, if I knew it's everything other than x being less than 1. So it's 1 minus the probability that x is less than 1. right? Because all of the probabilities should add up to 100% or 1. So the probability that x is bigger than or equal to 1, and in fact, let me just write it up here. This is a good time for a red pen. The probability that x is bigger than or equal to 1 plus the probability that x is less than 1 should add up to 100%. Because that's all the things that can happen. X can either be less than or equal to 1 or it can be bigger than 1. And that's kind of it. There's no other things that can happen. So then I can say, well, the probability that x is less than 1. This is where you have to be a little bit careful. When you're talking about discrete, it does matter if it's less than or less than or equal to. Right? Less than 1 means not 1. The only way you can get less than 1 tails is to have 0 tails. So this is 1 minus the probability that x is equal to 0. And that probability is 1/16. So it's 1 minus 1/16, which is 15/16. So typically, that's an easier way to calculate this. Right? You can say, oh yeah, I can calculate the probability that, right? Maybe, and it's better when it's like where it's more useful when you have more things. Like, for example, just to kind of extend this idea. So we're not going to actually calculate this. Well, we're not going to do all the calculations, but I'm going to ask you a question that's very much related. So let's say now I flip 10 coins. I actually want to, let's say I flip 10 coins. What's the probability that the number of tails is greater than or equal to 1? And calculating that the long way would be terrible, right? First of all, you have to find all the things and say, okay, it's the probability that x is equal to 1 plus the probability that x is equal to 2 plus all the way to the probability that x is equal to 10, where x is the number of tails. And that's not fun. I don't want to calculate all that. Instead, we say, well, I can use the complement. Say, well, this is the same as 1 minus the probability that the number of tails x is less than 1, which is 1 minus the probability. So x less than 1 is just x equal to 0. And the nice thing about 0 tails is there's only one way to get 0 tails. All tens. So there's one way to get 0 tails. How many ways are there? How many total different things are there that can happen by flipping 10 coins? How many different outcomes are there? I'll remind you, when we flipped 4 coins, there were 2 times 2 times 2 times 2, which is 2 to the 4th possibilities. So if flipping 10 coins, how many possibilities should there be? Anybody? Spare your fingers. Yeah, 2 to 10. Also, I watched Bring It On recently, again, for, you know, I won't say what number time. Movie doesn't exactly hold up. There's a few things in there that feel like oh, really? Okay, that seems a bit dated. On the other hand, Mean Girls definitely holds up. So this is 1 minus 1 over 2 to the 10th, which is 1 over 1,024. I mean, you can just leave it like this. It's going to be, you know, 1,023 over 1,024. Okay. So great. I think we've talked about expected value pretty well. We've talked about probability stuff. Let's move along and talk about variance, because when we're talking about probability, there's kind of 2 things there's a lot of things we care about, but 2 of the most important things are measures of center, and the mean is definitely one measure of the center. There are other measures of the center, which we'll talk about. I think it's section 9.2 and 9.3, called the median. And the difference between the median and the mean is the mean is like a weighted average, or the expected value, whereas the median is just the middle measurement. Right? So an average, really big values can count for more, whereas with the median, they don't. So like when we talk about household income, we often talk about the median household income because it's a measure of 50% of the population has an income above this level and 50% has an income below this level. Whereas if we talk about the average household income, we get skewed really far to the right because there are there are some outliers that make millions and millions and billions of dollars, and that really tilts the average this way. So we often talk about median as a measure of center because it can be more reflective of what's actually happening. It's not heavily influenced by outliers. The other thing we care about when we talk about probability and distributions is variability. And so there's a measure of variability called variance, and then along with that standard deviation. So here's how we calculate variance. Now let's go back to our coin example. So for our coin example, we have this table with 4 coins. Right, 4 coins, number of tails. We have this lovely table, x, p of x. Table. And we found that the expected value was 2. So the way you calculate variance is you're trying to measure how much difference there is from the mean. So things that are far from the mean should count for more, and things that are closer to the mean should count for less. So here's the way, and so there's lots of actually different ways of calculating variance, right? You could use the absolute value and say like, well, it's going to be the difference between my score and the mean in absolute value, right? Because we don't want the negatives and the positives to cancel that out. But the problem with absolute value is it's really not a nice function. It's kind of a pain in the butt. It's not differentiable. So instead, what people decide to do is they decide to use the variance. They take the difference between their score and the mean, and then they square it. So the way I calculate the variance here, let me actually go back to this example. Yeah. So, let me go back to, before I do this example, let's go back to the other example, which was our test scores example. So remember for our test scores, we had 0, 0, 100, 100, 20, and 80. And we found the mean to be 50. So the variance here, here's how we calculate the variance. It's the sum of the difference between your score and the mean squared. And the reason we're squaring is really so that actually it accomplishes 2 things. It accomplishes really kind of things that are further from the mean get to count for more because the difference is getting squared. And it also accomplishes everything being positive, right? Because we don't want to be like, well, the variance is 0 because we ended up all these positive negative things. So here, you're going to do that minus that squared, and then you're going to multiply by the probability of x. Again, the more things that you have, you can count them all up. So in this case, it's going to be 0 minus 50 squared times the probability of 0, which was 2/6, plus 100 minus 50 squared times the probability of that, which is also 2/6. So both 100 and 0 are contributing the same amount towards the variance because they're equally apart from the mean, and they also occur the same number of times. Plus 20 minus 50 squared times 1/6 plus 80 minus 50 squared times 1/6. Let's see, this math is going to be not particularly pretty. We could do it, but I'm just going to tell you it comes out to be about 1,967. Now, here's the problem with variance. These are test scores, right? And now I'm saying the variance is 1,967. 1,967. It's not particularly meaningful. And one of the reasons it's not is because the units are actually the unit square, right? I mean, not that the units really make a lot of sense here. Right? We're talking about test scores. Scores squared is kind of weird. So even though the variance is a measure of variability, it makes more sense and it's more useful to talk about the standard deviation, which is the square root. You use the symbol sigma is the square root of the variance. And in this case, that's going to be approximately the square root of 1,967, which is about 44 points. And that makes sense to some degree. I mean, that feels like kind of a big number in general, but we're saying, okay, this is a measure of how far each test score is from the mean, which seems reasonable, right? The mean is 50, and you got test scores that are way far away, 0 and 100. You got test scores that are a little bit less far away, 20. So it seems reasonable. Here, the way we calculate the variance is the same. It's going to be the sum of R squared minus the mean squared times the probability of that happening. Or really, I'm saying the number of times it happens. So here it's going to be, all right, so it's going to be 0 minus 2 squared times 1/16 plus 1 minus 2 squared times 4/16 plus, I don't even really need to write the next term. It's 2 minus 2 squared, which is 0 times 6/16. Something worth noting, scores that actually are the mean, right? So when you get scores that actually are the average, they don't contribute to the variance at all because they are not different. And then we get 3 minus 2 squared times 4/16, and then we get 4 minus 2 squared times 1/16. Adding this all up, so let's see, 0 minus 2 squared is 4, so 4 times 1/16, which is 4/16. 1 minus 2 squared is 1 times 4/16 is 4/16. I think this one, every term is 4/16, this one is 0. That's a 4/16, which is 1 times 4/16. And that's a 4/16. I think the reason we like this example is because the numbers sound nice. So here the expected value is 2 and the variance is 1, meaning the kind of average both. So the variance is 1, and then in this case, the standard deviation is also 1 because it's the square root of 1. So the average difference from the mean is 1. That doesn't mean the difference from the mean is always 1, it just means on average, like if you select something at random, on average, you're going to be 1 away from the mean. Sometimes you might be 2 away from the mean. Sometimes you might be 0 away from the mean. Sometimes you might actually be away from the mean. But on average, yeah. Let's see. I think we've got time. Yeah, we've got time for another example. So one place where expected value really kind of comes up is actually like games of chance, like poker, like the lottery, all sorts of things like that. So basically, kind of the idea of something is if the expected value, if you're playing a game of chance for money, and if the expected value is positive, it's a good bet. If the expected value is negative, it's not a good bet. So suppose a game is made in which a player receives, so the player gets $5 for flipping 3 heads or 3 tails. And they're flipping 3 coins. And loses $2 for anything else. For any other combo. So that could be 2 heads and 1 tail, or 1 head and 2 tails. Also, here's the attendance and stuff again. Please do fill out the attendance. It is important. So let's see. So is this game fair? I mean, that's maybe not the way I would phrase it. I would ask, what's the expected value? So is the game fair? Fair, I mean, fair to who? Fair to the person trying to win, or fair to the person running it? So what's the expected value of X, where X is the amount of money? Let's say X is the, right, is that what I want to say? Actually, let me say one thing. Yeah, X is the amount of money. Okay, so, well, I can either win money, so I can win $5. Right, so that's my X times what's the probability of winning $5? I know we didn't do a table for 3 heads or tails, but we can think, so how many total possibilities are there for flipping 3 coins? It's my favorite number, by the way. So 3 coins. How many possibilities are there? Yeah, totally 8. Right? It's just 2 times 2 times 2, or 2 to the third, which is 8. Okay, this is actually not too hard to calculate. How many ways are there getting 3 heads? So I think, Sophia, you're answering the question. You guys are both answering questions that I'm kind of asking. So the way of getting 3 heads is 1, and the way of getting 3 tails is 1. So yes, there's 2 total ways of getting what we want. So there's 2/8 probability of getting a win, right? 3 heads, 3 tails, there's 2 ways. So if I know there's 2/8 ways of getting a win, I know there's 6/8 ways of not getting a win, right? Because the other 6 things have to be not what I wanted. So we don't have to, what I'm trying to say here is we don't have to write out the whole list of all the 8 things. So the other X value, well, it's losing $2 isn't winning $2, so it's negative $2 times a 6/8 probability. So if this turns out to be positive, that means we should play, right? If it's a positive effective value and you've got infinite funds, you can just keep playing, and eventually over the long term, the averages will play out and you will expect to win. Let's see. So 5 times 2 is 10/8. Minus 2 times 6 is minus 12/8. So this is negative 2/8, which is negative 144, negative 0.25. So over the long run, we can expect on average with each time we play to lose a quarter. So this is a game we should not play. It's definitely a game that someone should run, right? If you were the person running the game, it would make sense to set it up this way. That's how most casinos are set up, right? Where the average long-term odds are in their favor, just like this. So that's kind of the idea there. And I really need to use the restroom, so I think, although there's 2 minutes left in class, we should call it a day. If you guys have questions, feel free to ask them in the discussion. I really appreciate that you guys are using the discussion in this class. I like it. It's a good place I can respond to it. My other classes, 17C has done all right using the discussions, and the other 2 not so much. So thank you for using the discussions, because I think it's a good forum. If you have questions, go ahead and ask them there, or you can always send me an email, but discussions are good. And there is the attendance stuff again. Make sure you fill it out. I'll see you guys next week. End of week 8. And I'll give you guys this quiz is graded today. I meant to do that yesterday, but I did write solutions and post them, but I haven't graded them yet. So they're up there if you want to see them. All right, that's all I got for you. Talk to you later.